In statistics, simple linear regression, also called simple regression, is a linear regression model with a single independent explanatory variable. In this video, we developed an equation to express the relationship between variables and conduct the linear regression analysis. In the previous video, we have discussed correlation and inferred that variables might demonstrate linear relationship. For example, in the correlation between advertising and sales, we may argue that advertising causes change in sales. In financing, an individual investment return normally highly related to the entire market return as well. To deeply understand the relationship between these variables, we can set up regression models by identifying some variables as the independent variables, sometimes also referred to as features or predictor variables, and some as dependent variables, also called response variable. Regression analysis is a statistical technique that uses observed data to relate the dependent variable to one or more independent variables. The dependent or response variable is the variable we wish to understand or predict. The independent or predictor variable is the variable we will use to understand or predict the dependent variable. The objective of regression modeling is to build a regression model that can describe, predict, and control the dependent variable based on the independent variable. In this sense, there are three main purposes of the regression modeling. The first purpose is to predict future value of the dependent variable when using values of independent variable. For example, we may use historical data to predict the impact of advertising on sales. The second purpose is to use the model to gain some insight, especially causal relationship between these variables, so we can better understand and explain certain phenomena. For example, we may use regression to determine if salary for computer programmers is related to the years of experience and the score on the firm's programmer aptitude test. The third purpose is to use the linear relationship to control the dependent variables. For example, after learning the relationship between sales and advertising, we may decide the advertising level to control and achieve our desired sales quantity. Simple linear regression attempts to model the relationship between two variables by fitting a linear equation to observations of these two variables. The equation has the form y equal to beta sub 0 plus beta sub 1 times x plus epsilon, where y is the dependent variable. That is the variable that goes on the vertical y-axis. X is the independent variable, which is usually plotted on the horizontal x-axis. Beta sub 0 is the y-intercept. Beta sub 1 is the slope of the line. And epsilon is the random error term. There are some assumptions in order to properly use simple linear regression. Here, we introduce four main assumptions. The error term accounts for the variation in the dependent variable that the independent variables do not explain. For the model to be unbiased, the average value of the error term must equal 0. A further assumption made by linear regression is that the residuals have constant variance. That is, their variance does not change across different levels of predictors. Otherwise, we encounter a problem called heterogeneity, which reduces the precision of the estimates. Linear regression assumes normality of the residual errors. So, inferential procedures for linear regression are typically based on a normality assumption for the residuals. However, as sample size increases, the normality assumption for the residual is not needed, following the central limit theorem. One observation of the error term should not predict the next observation. If you have information that allows you to predict the error term for an observation, you must incorporate that information into the model itself by adding an independent variable to the model that captures this information, which is no longer a simple regression though, but a multiple regression model to be addressed in other business analytics courses. Although we assume a linear relationship in the simple regression, we do not know the true values of these parameters in the above linear regression equation. We must use the obtained sample data to estimate these population parameters. In the estimation, given any observation of the independent variable, we have one estimate for the dependent variable. We also use B sub 0 to be the estimate of beta sub 0, and B sub 1 is the estimate of beta sub 1. In regression analysis, our objective is to use the data to position a line that best represents the relationship between two variables. The method used in these graphs that results in a single best regression line is called the least square principle. In theory, least square principle uses the data to position a line with the objective of minimizing the sum of the squares of the vertical distance between the actual y values and the predicted values of y. The line drawn in the leftmost chart is the best fitting line and is drawn using the least squares method. It is the best fitting because the sum of the squares of the vertical deviations is at a minimum. The sum of the squares is 24. The middle and the rightmost charts are drawn differently, and the sums of the squares is 44 and 132, respectively. Let us further explain the least squares regression. As illustrated in this graph, the error term is the difference between the observation value and the estimate predicted dependent variable's value. That is yi minus y sub I hat. The sum of the error squares is denoted by sum of square error, abbreviated as SSE, which is mathematically equal to summation of y sub I minus y sub I hat squared. Therefore, the objective of the least square error is to minimize the value of SSE. The general form of the linear regression line is the same as the equation of any line. In the formula, B sub 0 is the value of y when x equal to 0, and B1 shows the amount of change in y as x changes 1 unit. A positive value for B1 reflects a direct positive relationship between the two variables, and a negative value indicates an inverse relationship. In the first formula, B sub 1 equal to S sub xy over S sub xx. Well, S sub xy equal to summation of parentheses x sub I minus x bar parentheses times parentheses y sub I minus y bar parentheses, which is given by this extended equation. This is the sum of the product of the difference between x and its mean, and the difference between y and its mean. And the sample corrected sum of squares S sub xx equals summation of parentheses x sub I minus x bar parentheses squared, which is the sum of the squares of the difference between each x and the mean x value. After obtaining the values of b sub 1, we can then use the second formula, b sub 0 equal to y bar minus b sub 1 times x bar, to compute the intercept b0. The calculation of the coefficient b sub 1 might look scary. However, we may follow the computations steps by step. It can be done relatively easily in an Excel file. To showcase how to obtain these parameters values, please let us look at the following case study. In this case study, a real estate agent wishes to examine the relationship between the selling prices of a home and its size, measured in square feet. We collected a random sample of 10 houses, and the data are shown in this table. In the model, dependent variables y is the house price in $1,000, and independent variables x is the size of the home in square feet. A scatter plot of the two variables shows that there's a correlation between the two variables, and there might be some positive linear relationship between the two variables. To compute the parameters, we can obtain the mean values of the two variables at first, which is given by y bar equal 286.5 and x bar equals 1,715. Following the procedure, we get the value of x squared for each observation, y squared for each observation, and y times x for each observation. We can then compute the s sub xy and s sub xx values, which are s sub xy equal to 172,500, and the value of s sub xx is equal to 1,571,500. After obtaining the previous values, as shown in the upper part of this slide, we can then use the equation to compute the coefficient b sub 1 as follows. B sub 1 equal to s sub xy over s sub xx equal to 172,500 over 1,571,500 equals 0.1098. And b sub 0 is equal to y bar minus b sub 1 times x bar equals to 286.5 minus 0.1098 times 1,715 equal to 98.193. Therefore, we obtain the linear regression model, which is given by y equal to 98.25 plus 0.1098 times x. This is the way we get to the linear regression model before we have powerful enough computers and softwares. Nowadays, we have help from software, and the above procedure have been designed into the software to help us obtain the linear regression model in a relatively easy way. This table is obtained after using the Excel data analysis regression algorithm. As we can verify, the coefficients are the same as what we have computed previously. As we can tell from these coefficients, we have the model of house price equal to 98.25 plus 0.1098 square feet. In the following, we demonstrate how to obtain the linear regression model using Excel data analysis at the end. Before we go to the Excel file, here is the procedure. First, we select data area of the dependent variable. Second, we select data area of the independent variable. Third, we select labels if our data includes the labels. Normally, please do not select constant is 0 unless you are 100% sure that the constant should be 0. And then we select the confidence level to your design, for example, 95% by default or 99% if you want. Finally, we specify the area of the output. Now, let's go to Excel. You may pause here and open this file to make sure you can follow me step by step. Okay, as you can see from this Excel file, we already have the data ready here for those 10 samples. We have Y denotes the house price and X denotes the square feet. I repeat the procedure here so that you can follow in case. I already run the regression and have the output here. Before we rerun here, let me quickly point to these outcomes because we need them in the next 2 videos. Here, the first one, the first table is called regression statistics. Specifically, we have the R-square and standard errors here. So we have to come back on these 2 specific values in our next video. And the second table is about ANOVA. As you can see here, we have the regression, residual total, and we have the degrees of freedom, the sum of squares, and the marginal sum of square, and the f-test, the p-value of the f-test. We are going to come back on this table as well. And the last table, actually, I just showed you previously about the 2 coefficient values we obtained in the previous PPT slides. And we verified that we have the same coefficient values. Of course, you can run the scatter plot to get some sense of the correlation between these 2 variables, which is not required in the regression algorithm here. You can also print out the residual and the residual plot. I would like to point out that these residual output and residual plot are not required in this course. So in our next slides, we are going to talk about, we are not going to print this outcome just for simplicity. Because this page is already quite crowded, so we are going to use a new page, a new sheet to run the regression. So we have the same data here. As I said, we are going to call the data and data analysis. Okay, hopefully you follow me already here. So data analysis, and I say okay. And as you can see here, you are going to find there's one item called regression, right? we have only one choices of regression here. It means we have regression for simple regression and multiple regression in the future together in the regression model. So we're going to say, okay, now you're going to input the Y range. So we're going to collect Y range. Y range actually is the house price. We have, as we already have Y and house price, two kinds of names here. So we call only the Y. And we say, okay, the X value is the square feet. So we are going to call only the X and the square feet. And we say, okay, because we included Y and X as the labels, so we are going to click yes for the labels. As we previously said, we are not sure whether the constant is 0 or not. So please do not click on this one. Leave this one empty. By default, we are going to have confidence level 95, and that is what we want as well in this case. So we don't have to change it. Just say confidence level 95%. The output of residual is not required in this course, so you don't have to click on any one of them. So all we need to make sure we have the output range. Because this page is quite empty, so we are going to just say, okay, I'm going to put somewhere, probably here, right? That would be my output. So I'm going to say, okay. After doing this, I'm ready to say, okay. The printout actually is exactly the same as we comment on the previous sheet, like here. Although I highlight some number in colors, but that's exactly the same, okay? So we have R square, the standard error. Okay, and we have the ANOVA analysis. We have the coefficient, okay? So later on, we want to talk about more about this table. We are not going to come back to Excel to repeat these tables, but pretty much in the next two videos, we use the same data, exactly the same data in our discussion. In this video, we have formally introduced the simple linear regression model and show how to compute the parameters of the linear regression equation. We also demonstrate how to get the linear regression model using Excel regression algorithm. So please make sure you understand all these concepts and know how to use Excel to get the regression model.